we have seen like we need to go with the analysis of MOS semiconductor structure, that is metal oxide semiconductor structure. So in that we have seen like the MOS structure is made up of three layers basically. So one is gate, another one is oxide, and the third one is your semiconductor. So if there is no other external voltage applied to it, and no other combination is circuitry connected to this, then it will be considered as a two-terminal device. Like one terminal will be represented by the gate of the MOS structure, and the other terminal will be represented by the semiconductor. So these two conducting devices are there. One is metal, another one is semiconductor. In between that, oxide layer is there. So this uh, structure seems like a capacitor structure. So it works as a capacitor also. So this is the basic structure of MOS oxide metal oxide semiconductor structure, that is the resembling the semiconductor structure. Here the basic properties of semiconductor is like if a semiconductor is there, it will be having n-type charge carriers and p-type charge carriers. If the semiconductor is undoped, then the charge carriers is represented by Ni, that is intrinsic charge carrier, and this intrinsic charge carrier is having a fixed value at room temperature, that is around 1.45 into 10 power 10 per centimeter cube. So for intrinsic semiconductors, the Ni is fixed at room temperature or at particular temperature. The Ni is fixed. So if that intrinsic semiconductor is being doped by either p-type uh, material or n-type material, we are doping using elements to make either n-type or p-type. Based on that, what will happen, the doped semiconductor will be having some electrons, that is n-type semiconductors for electrons, and another one is holes. So the combination, that is multiplication, the multiplication of holes and electrons will be equals to Ni square, that is intrinsic charge carriers. So this law is called your MOS-Exxon law. So based on this MOS-Exxon law, if we consider the p-type semiconductor, p-type substrate, here we have used the semiconductor. So that in that p-type semiconductor, if we want to find out the number of electrons, so this is number of electrons in p-type semiconductor, and this is number of holes in p-type semiconductor. So number of holes will be considered as the Na, that is doping concentration of acceptor ions. So whatever acceptor ions are there, the number of acceptor ions, the concentration of acceptor ions being used to dope this intrinsic semiconductor to make it a p-type semiconductor. So from there, the number of holes will be given by this Na, similar to this, and the number of electrons in p-type semiconductor will be given by Ni square divided by Na. So this is the depiction from the MOS-Exxon law only. So basically we will deal with the energy band diagram of a MOS structure. Like a MOS structure is there, so what will be its energy band diagram and how that energy band diagram is formed. So in MOS, what we do is we combine three different layers: metal, oxide, and semiconductors. Okay, so we will see one by one, that is how the energy band diagram of metal, oxide, and semiconductors are being varied. So this is the energy band diagram of a p-type silicon substrate. So if this is the energy band diagram, so there are some points we need to consider, and we need to have some understanding, basic understanding. So this is in energy band diagram represented by the two bands, basically the conduction band and valence band. So in between the conduction and the valence band, the middle of conduction and valence band is represented by intrinsic Fermi level. So what is Fermi level? So Fermi level basically deals with the region in that energy band diagram where the finding the charge carriers is the probability of finding the charge carriers is around 50%. Okay, so this region is called intrinsic Fermi level. But once we dope this intrinsic semiconductor by either p-type or n-type dopant, what happens is, if after doping the semiconductor becomes p-type semiconductor, in that the Fermi level will be moving towards the valence band. Okay, that means the number of the probability of getting charge carrier in the form of holes will be higher in case of p-type semiconductors. Similarly, if it is doped by an n-channel n-type dopant, then the Fermi level will be at this region in between conduction band and intrinsic Fermi level region. Okay, so there are some points like q xi. This q xi represents the quantity called electron affinity. So what is electron affinity? So this is an energy band diagram of semiconductor. So it will be having a conduction band and valence band. Along with that, and free space energy band is represented by E naught. Okay, so this represents a free space. Like in a semiconductor element, there are some conduction band and valence band, but in free space, if free space energy band is represented by E naught, then the difference between the free space energy band and the conduction band energy band will be represented by Q into xi. Okay, so this Q into xi is called electron affinity. Okay, so it is represented by your electron affinity. So this is represented by electron affinity. Okay, so you have any doubt, we will be studying the electron affinity. So whatever electron affinity is there, we will see. So electron affinity basically deals with, it is the potential difference between the conduction band level. So this is conduction band. Okay, so the electron affinity represents the potential difference between the conduction band and the vacuum, or that vacuum is represented by a free space. So the whatever potential difference is there in between conduction band and free space will be considered as electron affinity. Okay, so this electron affinity is represented by Q into xi. Okay, so Q into xi will gives you that potential difference. Another concept that we use is the work function. So what happens if any band diagram is given, in that the region, or you can say the energy that is required for moving an electron from the Fermi level to the free space, if this is the region, so from Fermi level to the free space, so whatever energy is required externally to transfer, I can say generate an electron from the Fermi level to free space, this will be called as the work function. So there are two points we should be knowing to move further. So like one is electron affinity, another one is work function. So any metal or conductor is there, we need to find out the electron affinity as well as the work function. Along with that, we are having another concept that is called this phi f. So this phi f represents the surface potential. Okay, so what happens if there is a difference between these two. So the electron affinity and the Fermi level potential and the free space gap is called work function. In other words, is Q. So this phi f, that is represented as a Fermi potential. It is given by the difference in Fermi level, okay, difference in Fermi level and the intrinsic Fermi level. So what is the difference between the Fermi level and the intrinsic Fermi level will be given by Q phi f. Okay, this is Fermi potential something. Okay, so this we need to consider for further analysis. So this is the basic understanding. So this Fermi level, or we call it Fermi potential, is given by the EF, whatever Fermi level is there after doping to a semiconductor. The Fermi level can be either moving towards the valence band, okay, or it could be either in the near the conduction band. So this near the conduction band will be for n-type, this will be for n-type, and this is for p-type semiconductors. So based on the difference in the Fermi level, okay, and the intrinsic Fermi level. So whatever difference between Fermi level and intrinsic Fermi level is there, that will be represented by your Q phi f and this Fermi potential. So this Fermi level is multiplied by Q, that will be Q, this will be considered as Fermi potential. So once we are dividing it by Q, that means it will be in the form of volts. Okay, and if it is Q into phi f, this will be in form of electron volts. Okay, if we are multiplying with this will be in the form of electron volt. So whatever uh, and the energy band diagram gap is measured, that will be in form of electron volt. So if we are multiplying phi f into Q, that will be considered as the Fermi potential in electron volt. If it is only phi f, means we are dividing EF, that is Fermi potential minus intrinsic Fermi potential, divided by Q. If we are dividing it to Q, it will be considered as a unit of volt. So this difference you should be clear of. So from there, we have considered different points, like one is electron affinity, another one is work function. So work function is the difference between the energy uh, band levels, that is Fermi level and the free space, or in other words, we call it the energy required to move or release an electron from Fermi level, this level, to free space will be considered as work function. And similarly, in case of electron affinity, it is the energy, energy difference or the potential difference in between the conduction band and the free space. And this is your Fermi potential. It is the difference between Fermi level energy and intrinsic Fermi level energy. Okay. And similarly, we need to see the other energy band diagrams. Like if a metal is there, so in that metal case, this is your free space level. Okay, and this is the Fermi level. So here Q phi f represents the between energy required to move one electron from Fermi level to free space will be considered as the work function. Okay, so this is the work function of a metal. So per function of a metal, here metal is considered as aluminum. We are taking aluminum as a metal weight. So the Fermi level will be given by, sorry, the work function will be given by 4.1 electron volt for metal case. Similarly, if we are considering oxide, the oxide is the insulator. Okay, so it will be having an energy band diagram with gap of between conduction band and valence band. And here we are considering it as a 8 electron volt. So this SiO2 is considered as insulator having energy band gap of 8 electron volt. And this Xi, Qi represents electron affinity. So in case of oxide, the electron affinity is given by 0.95 electron volt. Okay. So this is for metal, and this is for oxide that we will be using. Another one is for semiconductor. So semiconductor we have already studied here. So in this case, semiconductor, the gap, energy band gap that is in between conduction band and valence band is around 1.1 electron volt. Okay, so if the energy band diagram is high, energy band gap is higher, that will be considered as an insulator. And if energy band, there is no energy band gap in metal because the conduction band and valence band are overlapped to each other. So it is having no energy band gap. In case of semiconductor, the gap is around 1.1 electron volt. In case of silicon, here considering silicon, in that case, the energy band gap will be 1.1 electron volt. And here Q psi for silicon, that is the electron affinity for silicon, is 4.15 electron volt, and this is the Q phi f, that is Fermi potential. Okay, Fermi potential will be, because it is of p type, so the Fermi level will be below the intrinsic Fermi level. If the Fermi level is above, that will be an n type. In that case, the Fermi potential will be this. So this will be your Fermi potential. So one thing we can note here is, in case of p-type semiconductors, the Fermi level is considered as negative. So in case of this Fermi potential, sorry, the Fermi potential. So Fermi potential phi f for p-type is given by Kt by Q. This is the formula to find out the Fermi potential. So it is Kt by Q ln Ni by Na. So this Na is the doping concentration of acceptor ions. Okay, so this will be a negative. So in case of uh, p-type semiconductor, the Fermi potential is given as negative because this will be less and this will be high. So ln less than something, less than 1 will be considered as negative. So overall, this phi fp will be negative. In case of n-type semiconductor, phi fn will be kt by q ln, here nd divided by ni. This is the formula for calculating the Fermi potential in case of n-type semiconductor. So here Nd will be doping concentration of donor ions. So this Nd will be higher than Ni. So overall Nd by Ni will be more than 1. So if it is more than 1, the Ln value of any value more than 1 will be considered as positive. So overall this uh, Fermi potential in case of n-type semiconductor will be considered as positive value. And this is Fermi potential, and also the work function that we have seen. So work function is represented by, so the work function that we call it is represented by Q phi S. Okay, so this work function is given by Q phi S. It is equals to Q psi, that is electron affinity. Okay, this is electron affinity, and along with that is the gap, because work function was the energy between here to here. So here to here it is electron affinity, and again is energy between these two. Okay, so this energy will be given by EC minus your Fermi potential. So EC minus Fermi potential will be considered as your this energy gap, and plus you will be doing the electron affinity. Overall, this will give you the work function. Okay. So these formulas are important. You need to consider, like Fermi potential is given by this, and then once we know the once you know the definition, what is Fermi potential and what is work function, you can directly derive its expression. There is no need to remember it. So as the work function definition says, the energy required to move an electron from Fermi level to free space. Okay, so Fermi level to free space. So it will be consisting of these two, this energy gaps. So from here to here, it is given by electron affinity. So from here to here, it will be difference between EC and EF. Okay. So this is your work function equation. So individually, we have seen like what is the energy band diagram of semiconductor, what is metal, and what is oxide. So based on metal, oxide, and semiconductor energy band diagram individually, we will combine it to form metal oxide semiconductor system, that is MOS system. After combining all the layers, we will be getting the energy band diagram of mass as the diagram shown in figure 3.3. Okay, so this is showing the energy band diagram of a combined MOS system. So here, one thing we should be knowing is the Fermi level of metal, whatever Fermi level of metal is there, the same Fermi level will be there for semiconductor also. So the Fermi level difference, there will be no difference. The Fermi level will be on the same level. Okay, so both the Fermi levels will be same, but there is some difference. Like instead of conduction band should be straight, it is quite bent. So why this bending is there? So once we are combining metal, oxide, and semiconductors, what will be there? There will be a difference because of difference of potential. So whatever potential is there at this surface, so this is a surface, this surface is the interface of metal and oxide. So this is the surface of metal and oxide, and this is the surface of semiconductor and oxide. Okay, so as there is the difference between the work function of a metal and the semiconductor. So in the previous one we have seen like the uh, work function of metal was 4.1 electron volt, and similarly if we find out the work function there, the work function of semiconductor will be something different than metal work function. Okay, so because of this work function difference, what happens, there will be a potential drop, or you can say there is a built-in potential in between the metal and semiconductor. So in across the oxide, there will be a built-in potential. Okay, so we call it VIN, built-in. VBIN built-in is दोनों में से कुछ भी बोल सकते हैं, ठीक. So this, because of the metal work function difference between metal and the semiconductor, there is the potential drop, or you can say built-in potential across the oxide. Okay, so this that potential difference will be called as built-in potential. And one thing we need to note is that at equilibrium, the Fermi level at equilibrium, after combining three layers, and after the equilibrium is reached, the Fermi level of both the materials, both the conductors will be off at the same level, but the energy bands of conduction band and intrinsic Fermi level and valence band is bent near the surface. So this benting is because the whatever built-in potential develops between metal and semiconductor, it is mostly across the oxide, but there is some voltage drop. This built-in potential value is also found across the surface area of the oxide and semiconductor. So this is the interface of your oxide and semiconductor. So some of the built-in potential also can be found near the interface of oxide and semiconductor. So because of this, there is a bending of energy bands of the semiconductor. So this bending is because of your built-in potential that is found near the oxide and semiconductor interface. Okay. So this region here, this is called your bulk region because your semiconductor, so like this is your metal MOS device. Okay, so this is your bulk region or substrate region. This is your bulk region, and this is your like gate region. Okay, so this is gate. In between that, oxide will be there. So this region will be considered as the surface region. So this is your surface region. This surface is between the oxide and the semiconductor. This is oxide and this is semiconductor. So this oxide and semiconductor interface will be considered as the surface region. Okay, and this beyond the surface, it will be considered as a bulk. Okay, so this complete will be a bulk. This complete will be a bulk, and the same semiconductor near the oxide will be considered as the surface region. So near the surface, there is a bending of energy bands of the semiconductor, but in the bulk region, this is the bulk region. In the bulk region, the energy band will not be affected. So whatever energy band of semiconductor will be there, it will be having very less effect. So almost it is constant. So no significant change is there, but the energy band near the surface, interface region will be changing. This changes because of some of the built-in potential develops across the interface region. Okay. So there is an example. So based on whatever formula we have seen, whatever concept we have seen, we will be having some example. So we are taking an example. So here, consider that example as, so a mass structure is there. Okay, so that is made up of metal, that is of aluminium gate, and that silicon dioxide SiO2 as oxide, and p-type doped silicon, okay, as a semiconductor. So the equilibrium Fermi potential of the doped silicon substrate is given by Q5F is equals to 0.2 electron volt. That means after combining all the layers, the equilibrium Fermi potential is found to be 0.2 electron volt. Okay, so using the electron affinity of silicon and work function for aluminum given it. So in the previous structure, we have seen like in 3.3 figure, we have electron affinity, sorry, work function of metal as this, electron affinity of silicon as this semiconductor. So that value we will be taking. Then we need to calculate the built-in potential. So we need to found out what is built-in potential difference across the metal oxide semiconductor system. So MOS system is there. So what will be the built-in potential we need to find out. And also we are assuming like assume the MOS system contains no other charges in the oxide or on the oxide silicon interface. So एक एग्जाम्पशन को कंसिडर किया गया है कि कोई भी चार्ज है वो सिलिकॉन जो ऑक्साइड है उसके अंदर कोई चार्ज नहीं है, और उस सिलिकॉन सेमीकंडक्टर और ऑक्साइड उसके इंटरफेस पे भी कोई अदर चार्ज नहीं है, सभी चार्ज जो है इनसाइड द मेटल है या फिर सेमीकंडक्टर है. ठीक है, दैट मीन्स देयर इज नो लीकेज विद द चार्ज, देयर इज नो लीकेज ऑफ चार्ज. So we need to find out the built-in potential. Okay, so built-in potential will be given by, so we have a structure like this. This is the individual representation. If we consider it a complete combination, so here this is the metal region, this is the semiconductor region. So we need to find out the potential difference. So this potential difference will be considered as the difference in work function. Whatever work function of metal is there and whatever work function of semiconductor is there, the difference in this work function will generate the built-in potential. So to find out the built-in potential, we need to find out the work function of either metal and the semiconductor. So in case of metal, the work function of metal is already given, that is 4.1 electron volt in the 3.3 figure. So we will directly take the work function of metal. So finally, we need to calculate the work function of semiconductor. Okay. So the work function of semiconductor, we can find it by the formula we have studied. So this is the formula, like Q pi s is the work function of a surface will be equals to Q psi, that is electron affinity, plus conduction band energy minus Fermi level band. Okay, so this is the formula we need to find out. So here we will calculate. So this one is the electron affinity. So electron affinity of semiconductor. So electron affinity of semiconductor is already given 4.1 electron volt in the figure 3.3. So we need to take electron affinity value from figure 3.3, and this is the work function value of metal. So work function value is already given 4.1 electron volt, and this is the electron affinity of semiconductor 4.15. So this work function will be given by, that will be given by electron affinity plus this is EC, that is conduction band energy, minus the Fermi level energy. Okay, so this uh, conduction band energy and Fermi level. So in the figure we will move again. So whatever uh, work function we will be calculating, we need to find out this value. So this value will be your कंडक्शन बैंड एनर्जी माइनस द फर्मी लेवल वैल्यू. ठीक है, बट हमें ये वैल्यू हमें पता है इन द क्वेश्चन Q5F we have been given. So Q5F for p type is given like 0.2 electron volt. Okay, so this is your Fermi potential. So Fermi potential is given in the terms of electron volt as 0.2 electron volt. So Fermi potential is given, so only we need to find out is this value. Okay, ये वैल्यू हमें फाइंड आउट करनी है, केवल ये जो अगर वैल्यू फाइंड आउट हो गया तो हम ये वर्क फंक्शन फाइंड आउट कर सकते हैं. सो तो ये वैल्यू होगी, दैट विल बी, ये हमें क्या दिया हुआ है, एनर्जी बैंड डायग्राम जो है, एनर्जी बैंड गैप, सॉरी एनर्जी बैंड गैप जो है वो 1.1 इलेक्ट्रॉन वोल्ट दिया है. तो एनर्जी बैंड गैप क्या होता है, कंडक्शन बैंड माइनस वैलेंस बैंड. सो कंडक्शन बैंड माइनस वैलेंस बैंड विल बी योर 1.1 इलेक्ट्रॉन वोल्ट. और हमें पता है कि जो इलेक्ट्रॉन एनर्जी लेवल जो होता है, इंट्रिंसिक फर्मी लेवल जो होता है, वो होता है मिडिल ऑफ कंडक्शन एंड वैलेंस बैंड. सो मिडिल ऑफ कंडक्शन एंड वैलेंस बैंड EI होता है, दैट इज इंट्रिंसिक फर्मी लेवल. दैट मीन्स इफ इट इज कंप्लीट इज 1.1 इलेक्ट्रॉन वोल्ट, सो द मिडिल वैल्यू, so this value will be of 1.1 divided by 2, that will be 0.5 electron volt. Okay, so it will be 1.2 divided by 2, that will be 0.5 electron volt. So 0.5 electron volt plus this value, this is given by 0.25, sorry 0.2 electron volt. So total will be given by 0.7 electron volt. Okay, so EC minus EF will be given by 0.7 electron volt. So after combining, we will get 4.9 electron volt as the surface work function of your semiconductor. So once we know this work function of semiconductor and we already know the work function of metal, so the difference between work function of metal and the work function of semiconductor will be giving the value of built-in potential. Okay, कोई डाउट है किसी को? So from there we can find out the built-in potential of this MOS structure, that will be equals to minus of 0.8 electron volt. Okay, so this is your built-in potential. So another point we can note from this question is like, if a voltage corresponding to this potential difference is applied, suppose this is 0.8 electron volt. So because of this 0.8 electron volt, जो हमारा एनर्जी बैंड डायग्राम है मॉस सिस्टम का, वो बेंड हो रहा है यहाँ पे। ये जो बेंडिंग है वो बिकॉज ऑफ दिस 0.8 इलेक्ट्रॉन वोल्ट की वजह से है। ठीक है, सो हम क्या कर सकते हैं, अगर हमने एक्सटर्नली कोई अप्लाई किया वोल्टेज गेट टर्मिनल पे जो कि 0.8 इलेक्ट्रॉन वोल्ट से ज़्यादा हो, ठीक है, अगर हमने 0.8 इलेक्ट्रॉन वोल्ट से ज़्यादा अगर कोई गेट पे अप्लाई करेंगे वोल्टेज, सो क्या होगा, ये जो बिल्ट इन पोटेंशियल है वो धीरे धीरे रिड्यूस होगा। ठीक है, जब ये रिड्यूस होगा तो एक टाइम ऐसा आएगा जब ये 0.0 हो जाएगा, दैट मीन्स टोटल 0 हो जाएगा। सो बिल्ट इन पोटेंशियल अगर 0 हो जाए उस टाइम पे जो एनर्जी बैंड डायग्राम होगा क्या होगा, उसमें कोई भी बेंडिंग नहीं होगी। जैसे जैसे हम यहाँ पे वोल्टेज बढ़ाएंगे, सो ये जो बिल्ट इन पोटेंशियल है वो धीरे धीरे रिड्यूस होगा। यहाँ पे पॉजिटिव हमने वोल्टेज अप्लाई कर दिया, ठीक है, गेट टर्मिनल पे, ये गेट है और ये सेमीकंडक्टर। सो गेट पे अगर हमने कोई पॉजिटिव वोल्टेज अप्लाई किया तो इसका जो बिल्ट इन पोटेंशियल है, बिल्ट इन वोल्टेज है, ये धीरे धीरे रिड्यूस होना स्टार्ट होगा और ये 0 हो जाएगा जब हम अप्लाई करेंगे 0.8 इलेक्ट्रॉन वोल्ट। ठीक है, अगर हमने 0.8 इलेक्ट्रॉन वोल्ट अगर अप्लाई कर दिया, सो यहाँ पे जो बिल्ट इन पोटेंशियल होगा वो 0 हो जाएगा। अगर बिल्ट इन पोटेंशियल 0 हो जाएगा तो उस केस में जो हमारा एनर्जी बैंड डायग्राम होगा द मॉस कंबाइंड मॉस सिस्टम का, वहाँ पे कोई बेंडिंग नहीं होगी। सो यहाँ पे कोई भी बेंडिंग नहीं होगी। ठीक है, सो कोई बेंडिंग नहीं होगा, इसका मतलब ये एनर्जी बैंड डायग्राम क्या होगा, फ्लैट होगा। ठीक है, सो एनर्जी बैंड डायग्राम फ्लैट होगा, सो दैट्स वाई वी कॉल इट फ्लैट बैंड वोल्टेज। सो वो वोल्टेज जो हम गेट पे अप्लाई करेंगे सो दैट कि हमारा एनर्जी बैंड डायग्राम जो है सेमीकंडक्टर का वो फ्लैट हो जाए, दैट विल बी कंसिडर्ड एज फ्लैट बैंड वोल्टेज। ठीक है, क्लियर है? किसी को कोई डाउट इससे अभी तक? तो नेक्स्ट पॉइंट है हमारा द मॉस सिस्टम अंडर एक्सटर्नल बायस। तो अभी तक जो हम एनालिसिस किए थे वो क्या था, हमने मॉस सिस्टम को मेटल ऑक्साइड और सेमीकंडक्टर को कंबाइन किया एक साथ, लेकिन हम उस पर कोई भी वोल्टेज अप्लाई नहीं कर रहे हैं। ठीक है, अगर हम उस पर कोई वोल्टेज अप्लाई नहीं कर रहे हैं, so in that case it will, after combining the metal and semiconductor, there will be a built-in potential across metal and semiconductor। so जब भी हम दो मेटल और सेमीकंडक्टर और मॉस ऑक्साइड को एक साथ मिलाते हैं, so there will be a built-in potential। okay, and this built-in potential will remain the same throughout the system until we apply some external positive or negative voltage। ठीक है, सो अभी तक हमने एनालिसिस किया विदाउट अप्लाइंग एनी वोल्टेज। नाउ वी विल एनालाइज द सेम MOS system for applying a external voltage। so what will be the effect of applying the external voltage on the metal oxide semiconductor, we will see in the next lecture।